Perfect. Okay, thank you, everybody. We're going to start the final session of the day. So please take your seats. The last session that we have today is the virtual lightning posters. Rather than showing the posters themselves, we actually gave the speakers 5 minutes to give their 5-minute pitch of their poster. We have a lot to get through, so this is going to be pretty rapid fire, but I think it's going to be really exciting to see all the very interesting posters. So I think without further ado, I will introduce the first poster. Oh, I want to note too, I'll remind people who is a student. So please, again, make sure that you put in to judge the poster so that they can be eligible for the award. Our first speaker is Jessica Badgley. She is a student, and she will be talking about inferring Antarctic ice sheet elevation change from temperature-sensitive ice core records.
My name is Jessica Badgley, and I'm a graduate student at the University of Washington. Today, I want to share with you an introduction to my work on inferring Antarctic ice sheet elevation change from temperature-sensitive ice core records. This work has been done in collaboration with Marina Dutch and my advisors Eric Steig and Greg Hakem. Ice core records are a source for continuous high-resolution estimates of polar temperature over glacial interglacial cycles. However, to directly compare them to other temperature-sensitive records, one must account for changes in the ice surface elevation. Thus, my overall goal is to disentangle elevation and climate signals in ice core records. I focus this project on Antarctic ice cores and temperature estimates of the LGM. This figure from Bizert and others' 2021 paper shows a compilation of LGM temperature reconstructions for 7 Antarctic ice cores. A continuing question that I seek to contribute to is, how much of the temperature difference between these cores is due to adiabatic effects of elevation change, and how much is due to differential impacts of other climate forces? In this project, I use an ensemble of climate simulations to evaluate the applicability of a method that is common in the broader paleoaltimetry literature, but has only been explicitly applied to ice cores a handful of times. The paleotemperature method assumes that the difference in past temperature between two selected sites is due to different elevation histories. Thus, the elevation can be estimated by scaling the temperature difference by an inverse lapse rate. An example of this is shown in the figure on the right from Steig and others 2001 for the Bird and Taylor Dome ice cores. Key assumptions of this method are that the sites experienced the same climate change, that the differences in temperature at the two sites are due to adiabatic elevation effects, and that the lapse rate is known. Users of this method go to great lengths to show that their sites likely experience the same climate change. The assumption that the lapse rate is known, however, has proved trickier to agree upon. The lapse rate in the paleotemperature method remains uncertain. So, in the mid to late 1990s, Forrest and others put out 2 papers trying to solve this question by removing the temperature lapse rate from the equation entirely. To do this, they turned to the first law of thermodynamics and created the paleoenthalpy method. For several reasons, I choose not to use the paleotemperature or the paleoenthalpy methods, but instead I follow the lead of Forrest and others to derive a very similar method from the first law of thermodynamics, but for which the lapse rate is known. With a few simplifying assumptions, for example, the hydrostatic approximation, the first law of thermodynamics can be rewritten to be a decomposition of temperature change into an adiabatic term and a diabatic term. There's a third term that I call the advection term that I won't talk about now, but I'd be happy to talk about with anyone later. The figure shows an example of how this decomposition looks when applied to a climate simulation of LGM to pre-industrial temperature change. From this equation, I derive the paleothermodynamic method, which is an equivalent method that has a known lapse rate. I apply this method to an ensemble of climate simulations to evaluate the uncertainty associated with applying it to Antarctic ice core records. Here's an example of one of my figures showing the estimated relative elevation change, its error, and the signal-to-noise ratio for ice cores and other locations around Antarctica. The take-home point of this figure is that the uncertainty is up to 1,000 plus meters and thus the signal does not emerge from the noise unless the elevation change is quite large. Marina Dutch additionally ran some CESM1 simulations that allowed me to separate the influence of elevation versus other climate forcings on the temperature change. Here's the same for the adiabatic component and the same for the diabatic component. This set of simulations has allowed me to dig even deeper into the source of the error in Antarctic LGM elevation estimates using the paleothermodynamic method. If you'd like to talk about any of this, have any feedback, or would like to see more of my results, please reach out. Thank you for your time.
Yes, and I also should have mentioned that we will have time for discussion with the virtual poster folks tomorrow. So hold your questions for tomorrow unless they're burning, and you can put them in the chat online. Okay, next up is Grace Barchek, and she will be presenting How Strong is a Sticky Spot? New Constraints on Healing and Shear Strength Beneath Willen's Ice Plain.
Hi, WAIS Workshop. My co-authors and I have been looking at basal sliding during stick slip of Willen's Ice Plain over in West Antarctica, and we find some interesting differences between basal sliding inferred from seismicity and surface motion recorded by GPS. Willen's Ice Plain is this fun glacier that moves by stick slip, which you can see in this 3-day-long GPS record. And if we zoom in on one of these slip events and we look at GPS data and seismic data recorded at the same place on the large sticky spot in the middle of the ice plain, we see some pretty interesting stuff. So over here on the left, we're looking at a single slip event, one of those surges, and an hour of data. The top panel is GPS motion downstream in black. The middle panel shows the GPS motion differentiated to velocity in gray, and the blue curve shows integrated seismic power above 1 Hertz recorded by a seismometer in the same location. And then on the bottom, we have a spectrogram of the seismic data showing the power at a range of frequencies through time. And so what we see in this data is that at the start of a slip event, the GPS begins moving downstream all of a sudden. The velocity increases and then decreases again. And this is all totally normal GPS data for a slip event. But the seismic power, on the other hand, it barely picks up at all when the ice begins moving according to the GPS. And in fact, it stays really quite low. It's really quiet for a solid 4 or 5 minutes, maybe into the slip event, before suddenly increasing in time. And we think that this offset probably results from the ice base being loaded, being locally locked and not sliding for a few minutes at the start of an event, while the ice column is being loaded by nearby ice that has begun sliding. So let me illustrate. Here is a cartoon cross-section of the ice stream moving from left to right, and a GPS and a seismic instrument installed next to each other at the surface. In the 10 or so minutes before the slip event, nothing is moving, there's no basal sliding, there's no seismicity, and there's no GPS motion at the surface either. Once the slip event begins, neighboring regions of the ice stream have started sliding, but the ice directly under the instruments is still locked and unmoving, which results in loading and deformation in the ice column as a result of this nearby ice motion. In the simplest picture, we might think of this as a shear strain in the ice, a shear deformation. And this shear strain can be converted to a stress and will exert some amount of shear stress on the ice base locally, depending on how you think the ice behaves. Eventually, after a few minutes and a few tens of centimeters of surface motion, the shear stress from that deformation in the ice column becomes large enough to overcome the local yield stress. Basal sliding begins and basal seismicity begins to pop off, which creates this sudden jump in seismic power. So when the seismic power increases, that's when we think basal sliding has finally begun. So this is neat because we can measure how far the surface moved, assume the ice base did not move, calculate the shear stress in the ice column as a result of the deformation using some assumption about ice rheology, and then estimate the local basal yield stress. So that is pretty neat. If we measure this pre-seismic deformation on GPS from the 2 sites that show this offset for a couple dozen events, we find that that pre-seismic offset can be up to nearly 30 centimeters of ice motion, which can happen before basal sliding begins. And also the magnitude of that deformation increases when it has been longer since the previous slip event. Next, if we assume a reasonable ice thickness and calculate the equivalent shear stress for that magnitude of strain for both of these 2 sites that show this, we can calculate the shear stress when it starts to move finally. So assuming the ice is elastic, we get basal shear stresses at failure that range from 200 kilopascals to nearly a megapascal for both sites, which might be a little bit high. If instead we create a simple viscoelastic model and we drive it using that GPS surface displacement, we find basal shear stress failure in the range of maybe 50 to a few hundred kilopascals, which might be a bit more reasonable for this part of Woolens, which is sort of the stickiest, so to speak. And we also see that even with the viscoelastic model, the yield stress still goes up when it has been longer since the previous event, which is a lovely little signal of fault healing. So quickly to summarize, see that basal seismicity and surface deformation are offset in time, which we suggest results from a locally locked ice base at the start of stick slip. And then we use that inferred deformation in the ice column to calculate the local basal yield strength, which turns out to be a function of how long it has been since the previous event. Thank you for listening, and if you find this interesting or if you just want to talk about glacial seismology, please get in touch. My email is up there in the corner. Thank you.
Great, thanks. Next, we have John Eric Christian, disentangling the roles of natural variability and anthropogenic forcing in driving rapid outlet glacier retreat.
Hi, everyone. My name is John Christian. I'm a postdoc at Georgia Tech, jointly in UT Austin. And I'm going to share some recent work that I've been doing with Alex Roble and Jenny Catania. We've been focusing on understanding outlet glacier retreats in the context of natural climate variability and trying to develop a framework for quantifying the anthropogenic role. So as we know, outlet glaciers in both Greenland and Antarctica have retreated dramatically, especially in the last few decades. And there's been a lot of progress in understanding the proximate mechanisms that have driven these retreats. For example, we know that decadal ocean variability appears to be a major factor in many settings. And although we're getting a better handle on the long-term trends, the forcing is still very noisy, and the anthropogenic component of the ice dynamic response is still quite uncertain. So one of the things that makes this challenging is the relationship between ice dynamics and bed topography. Most of the large retreats we've seen have occurred after the terminus or grounding line is pushed off of a bed peak, where it then retreats rapidly through deeper water. This is just one example shown here in West Greenland, but there are many others. And of course, we also have a theoretical basis for this instability on reverse slopes. And now the evolution of retreat may be different in every setting, but the general point is that this punctuated dynamic response has to be considered when trying to attribute the retreats we've already seen. So to illustrate why this is tricky in a noisy climate, we consider an idealized glacier here, whose terminus is sitting just past a peak in the bed topography. And if we force it with random decadal ocean variability, it bounces around on the seaward side of the bed peak for a while, but then it abruptly retreats. And I want to emphasize there's no long-term trend here. This is just an unlucky string of random climate anomalies that caused it to retreat. So how do we distinguish rapid retreats driven by noise versus an anthropogenic trend? Our approach has been to think about this probabilistically. That is, what's the likelihood that variability will push a glacier terminus off of a bed peak over some interval of time? And we can estimate this with large ensembles of model simulations, where each member is identical except for a different realization of random variability. So here's what that looks like with the same idealized glacier. We're looking over 150 years, roughly equivalent to the industrial era. And in this example, we're counting up the simulations where the glacier retreats more than 4 kilometers behind the bed peak. And in this case, we see about a 10% chance of sustained retreat due to variability alone. Now, this likelihood corresponds only to the synthetic scenario, of course, but it illustrates the basic null hypothesis. Now, the real key for attribution is comparing simulations with and without anthropogenic forcing. So let's consider the simplest scenario, just a simple linear trend over the industrial era. This is one realization, and you can see that the trend isn't very big compared to the variability that we've imposed. But if we run ensembles for each scenario, we can see that the trend dramatically increases the probability of retreat. Again, this is only a synthetic case, but the point is that even a weak trend can really change the likelihood of retreat. By the same token, that means that conclusions about attribution could be quite sensitive to what we assume about the forcing. So say we assumed a different scenario where the same magnitude of forcing was applied, but only over the last 50 years. This still increases the probability of retreat, but much less so. So this would be a weaker attribution statement. The big difference is all about the glacier integrating its forcing or integrating, in the ensemble case, the difference between the scenarios. So even if it's weak, the early stages of anthropogenic forcing may be very important for drawing conclusions about attribution because ice dynamics have had more time to integrate those early changes. So to summarize, we're proposing a probabilistic framework for attribution where we ask what's the likelihood that climate variability alone could drive retreat from a bed peak, and how has anthropogenic forcing changed that probability? Beyond this basic framework, the main takeaway I want to leave you with is that even modest external forcing trends may really increase the probability of retreat for a glacier sitting on a bed peak. And this is just basic ice dynamics. If we're dealing with a system that integrates forcing on multi-decadal to centennial timeframes, we can expect this is going to be a robust effect. Of course, the exact numbers are going to vary by setting, but I think framing attribution probabilistically is a way to highlight this. So thanks for watching, and please feel free to reach out with any questions.
Thank you. Okay, reminder, the next presentation is by a student, Martin Forbes, flexing the explanatory power of plane strain in a grounding zone shear margin.
Good afternoon. My name is Martin Forbes. I am a PhD candidate at the University of Otago in New Zealand, and welcome to this flash talk on 2D flexural models of the Priestley grounding zone shear margin. Okay, so the 15-second backdrop to this study is that 2 years ago, a New Zealand-led group of scientists went down to the Priestley shear margin and carried out a suite of measurements over roughly 2 to 3 weeks. In these measured data sets, there are two that we will focus on today and that we will compare to modeling results. So the first is continuous GNSS positioning of the camp over the course of those 2.5–3 weeks, which you can see here broken down into three components: across flow, along flow, and vertical. And here in the backdrop you have a modeled tidal forcing. The second data set is this very impressive total station measurements that were carried out over 4 or 5 days that give a very accurate measurement of the strain on the surface of the glacier out to 200 meters and 1,200 meters in red from camp. Okay, so on to the modeling. So as I've already mentioned, this is going to be a simple elastic model, 2D plane strain model that goes across the Priestley Glacier. So this model was implemented in Phoenix. The lateral boundaries were fixed, and this makes sense because in the lateral margin where we have velocity data, it tends towards 0 as we approach the margin. So here we have 4 hipsters on top of Priestley Glacier, and then their relative motion is plotted out in this plot here below. The glacier isn't forced here, so they're relatively motionless. So when we have a positive tidal forcing, most of the hipsters go up. The hipster in the middle goes just vertically up, and the hipsters between the middle of the glacier and the far margin move towards the left. And then when we have a negative tidal forcing, the hipsters go down and some of them move to the right. Okay, so now we're ready to look at a whole bunch of model results. Okay, So this first example we're going to look at is the simplest. So we have a homogeneous material property. It's 3.5 gigapascals. The Young's modulus is. And we're forcing the bottom with the tide, and both sides are fixed. So this is exactly the conditions under which we saw the hipsters. So under these conditions, the vertical surface deformation is this red line, and that across flow displacement is this blue line here. And you can see the magnitude of the displacement in these plots here. This is for the negative tide. And then in these plots, we're comparing the GNSS measurements with the outputs of this same model run in a dynamic fashion, so forced using a tidal model. Okay, so awesome job. We've represented the motion fully, or have we? Okay, so in this plot, we have in blue the strain out to 200 meters on that surface, the difference between high tide and low tide, and the difference between high tide and low tide of the strain out to 1,200 meters. And in the dashed lines, we have the expected values from the total station measurements. As we can see here at around camp, we are way off. So actually, we're seeing compression on the surface when we measured extension, and we're seeing extension at the surface when we measured compression. This means that in the model, camp is actually in the wrong part of the flexion curve. So we can play around with some of the parameters and see what kind of conditions would lead camp to be in the right part of the curve. So here we're also going to consider the possibility that the ice at the margin is much softer. So here we have two material properties. We have a stiffer overall glacier, and we have a softer margin. And the strain rates are even closer to those measured. In this last example, we pushed those two material properties, or Young's moduluses, to kind of the extreme. And here, although we don't perform much better at camp, we can see some of the conditions under which we get similar strains in the model than those that were measured in the field.
Coming up next, we have Cohen-Hofstede, Known Unknowns, the Characteristics of the Ice-Ocean Interaction of the Ronny Ice Shelf.
Hello, welcome to my talk. My name is Konovster. I'm a field glaciologist at Alfred Wegener Institute, AWI, in Germany. I'd like to present a project AWI is working on, Known Unknowns, the Characteristics of the Ice-Ocean Interaction of the Ronny Ice Shelf, also abbreviated as RISP, the Ronny Ice Shelf Project. AWI is looking for interested collaborators, so if you think you'd like to participate after hearing my story, please let us know. We are at an early stage in this project, seeing if there is interest in the international glaciological community to collaborate. Ice shelves are the floating part of ice sheets, and it is here that the ocean water is in contact with the ice sheet. Ice shelves exert a buttressing force on the upstream grounded ice, and this largely determines the ice flow velocity across the grounding line, and thus its contribution to sea level rise. Basal melt of the ice shelf is caused by sub-ice shelf ocean circulation, which is largely determined by the geometry of the ocean cavity. Usually these geometries are poorly known, and this was also true for the Ronne-Filtner ice shelf, the second largest ice shelf of Antarctica. To address this problem at Filtner Ice Shelf, AWI, in collaboration with the British Antarctic Survey, performed the Filtner Ice Shelf Project, FISP, between 2014 and 2017. Here they collected oceanographic data from under the ice shelf through several boreholes. They also collected the sub-ice shelf bathymetry with seismics and the basal melt rates with AP-RES. But the ice-ocean interaction of the Ronne Ice Shelf is still largely unknown, partly because the geometry of this ocean cavity is poorly known. And so part of RISP, the Ronna Ice Shelf project, will be to map the geometry of the ocean cavity of the Ronna Ice Shelf. We propose to do this by collecting continuous 800-kilometer long seismic profiles between Institute Ice Stream in the south and Ronna Depot in the north. In 2025, our seismic equipment should be at the Institute Ice Stream and will have to be picked up at Ronna Depot at some stage. So we proposed 2 tentative routes to collect continuous seismic profiles to get there. This will not only provide the ocean cavity geometry at these profiles, but also allow for paleo ice sheet reconstruction, as at these profiles we can determine the physical properties. We think we can easily collect one 800-kilometer long profile in one season. Why? It's because AWI has a very fast and effective way to collect seismic data. Since 2009, AWI uses a seismic vibrator in combination with a snow streamer. This turns a labor-intensive, slow land seismic operation into a fast marine seismic operation. We pull the vibrator and snow streamer by piston bully and can take a record every 30 seconds. Like this, we can easily collect 7-fold data over a 40-kilometer transect per day. AWI has done this at several ice shelves, as shown below, with good results. In 2010, we started at Extremisen, continued at Extremisen between 2016 and 18, giving a detailed submarine ice shelf bathymetry. And in 2017, we did the same at Vilkner Ice Shelf. Now we'd like to do this at Ronna Ice Shelf. A seismic dataset like this will improve the bathymetry of the ocean cavity, but it will also connect to existing marine seismic data profiles in the Weddell Sea. Datasets we'd like to collect are airborne magnetic and gravimetric data. They will benefit from the seismic data because they can be tuned with the seismic data, as here we know the ice thickness and the thickness of the water column. But we also think of UAV surveys, of sub-ice shelf sediment coring, of AP rest stations to measure basal melt rates, and of course of sub-ice shelf oceanographic data like CTT profiles, ocean current measurements. Suggestions here are very welcome. So what is the possible timeline of this project? The first possible field season would be in 2025-26, a while away. Before that, our seismic equipment is used in 2 other projects shown here, but it is good because we need the time to set up the logistics and depots. So if you're interested in participating, please let us know. Drop me an email. I look forward to hearing from you, and thanks for your attention.
Thank you. Next up, we have Nick Holshue. Is material strength expressed in geophysical properties of the glacial substrate?
Hello. For those of you I haven't met before, my name is Nick Holshue. I'm an assistant professor of geology at Amherst College. And I'm really sad that I can't be there in person with you all. I really like the WAIS Workshop. It's a great meeting. But today I'm presenting remotely on some work I've been doing with undergrads here at Amherst looking at radar data in West Antarctica. Our goal is really to address some fundamental questions around glacier sliding and determine whether or not there's any additional information encoded in radar imagery of the bed of glaciers that can help us understand some really uncertain processes that govern glacier change. So this is in part motivated by the uncertain parameters that go into our physical equations for ice flow. I have them categorized over here in boxes on the left. You can think about 2 of them as just material properties, a strength of the ice and a strength of the bed that are potentially constant or temperature dependent. But those things go into our equations that govern glacier sliding. And those equations, our basal sliding law, is also itself uncertain. Some people parameterize it as a linear viscous process. Some parameterize it as a plastic process. Some use mixed physics or spatially heterogeneous sliding laws. Historically, we have not had enough information to constrain all of these unknowns. And so we assume a sliding law, and then we use things like ice thickness and ice flow speed to invert for the strength of the ice and the strength of the bed. But as as the poles become more information rich, both from time-dependent satellite observations and from denser geophysical observations of the subsurface, it would be ideal if we could use this new information to further constrain the problem. The time-dependent observations are great at constraining locations that are dynamically changing today, where we see the ice thickness change or the flow velocity change. They can be fed into inverse models to help tease apart differences in the flow law. But those observations can't help us understand glacier dynamics in the interior where we aren't seeing these dynamic changes driven by the ocean. So if we can use the time-dependent observations to tease apart basal properties near the coast, we can compare those with geophysical observations of the subsurface and determine whether any of these things we can actually observe using acoustic or electromagnetic waves are predictive of the material properties and the resulting dynamics at that ice rock interface. We focus here for this project on signs of soft sediment deformation. So in 2009 and 2010, high resolution radar imagery were collected at 2 locations in West Antarctica at Thwaites Glacier. Together with swath radar processing techniques allowed us to produce really fine resolution DEMs of the glacier substrate. And what we saw in those areas were really interesting indicators of soft sediment deformation. These lineations within the substrate oriented in the same direction as ice flow. Not all of the radar data collected in Antarctica is capable of this swath processing. You need a wide enough array on the plane, multi-element array. But we have all of these surveys that were collected, for example, on the P3 during Operation Icebridge with a narrow array, or using the accumulation radar, the Croesus accumulation radar, which doesn't have as wide a number of elements. And so the question is, can we use any information we gleaned from the swath data to better interpret those radar images that we can't swath process? One thing that we see is that in areas where we have lineations, which we interpret as soft sediment deformation, it appears in nadir radar imagery as these parallel lines within the subsurface reflector. So you can imagine this blue curve up here is the cross-sectional topography. If we're flying into and out of the page, you get reflections off of all of the peaks. And if you're flying in the orientation of those lineations, they appear as these repeating reflectors in a nadir image. So our goal was to reinterpret the Croesus OIB archive to see where we may have evidence of soft sediment deformation and see whether or not that's related to glacier thinning that we see elsewhere in Antarctica. So to start, we pulled out the full OIB Croesus archive, and this is sitting over Thwaites Pine Island Glacier, this region here. And in order to use this method, the flight orientation needs to be roughly aligned with what we expect the lineations should be. So we subset that to just the data that's oriented in the ice flow direction, which is about 14% of the overall archive. So we spent time looking through these images, looking at the basal reflector to see whether or not we have any of these nice bed parallel horizons that indicate lineations. And what we found is only in a very small number of places do we actually see evidence of these bed forms. Curiously, they're in places we've already looked in detail. These are these 2 radar grids that I was just discussing collected over Thwaites Glacier. ISTAR data collected as part of the British ground geophysics over Pine Island covered 2 of these areas where they also see lineations, but not in many other places where we have flow aligned data from airborne campaigns. So our goal was to determine whether or not thinning patterns at Thwaites and Pine Island show any correspondence with areas of observed soft sediment deformation, maybe indicative of a plastic bed where the bed is very weak. Unfortunately, because so little of the data includes bed forms near the grounding line, we don't have a lot of information in areas where the dynamic change is most apparent. But as the ISAT-2 record increases in length as we collect more and more data, the signal of dynamic mass loss in the interior of Thwaites is becoming more apparent. So this leaves us with a number of questions. What is their correspondence with thinning? Do we expect that maybe stresses in those areas are fixed by a yield strength? Or can we generate new gradients and stresses in, for example, a linear viscous system? So that's what we're really thinking about with this project. I'd love to discuss it more with you on Wednesday. So please stop by if you have questions. Thanks.
Thank you. Our next virtual poster is from Tom Hudson. Ice quakes measure friction and slip at the bed of Rutherford Ice Stream, Antarctica.
So I'm going to talk to you today about using ice quakes to quantify basal slip and sliding behavior at an Antarctic ice stream. So the ice quakes we're going to look at today that are going to provide an observation for these sliding properties are ice quakes generated by ice sliding over the underlying till or bedrock. And as this ice slides over the underlying till or bedrock, it can generate seismic energy, which is released to the surface, and we observe as an ice quake. And we're interested in this sliding mechanism because it is presumably the predominant mechanism by which ice travels from the fast-moving ice streams in Antarctica to the oceans, promoting sea level rise. And we think the sliding at these ice streams is much, much greater than the deformation. So sliding is the dominant process and therefore the important process by which this ice enters the oceans, or controls the amount of ice at the speed of the ice entering the oceans. And we have a problem though here. So this is a statement from a paper in 2010 that says basal drag is a fundamental control on ice stream dynamics, but it remains poorly understood or constrained by observations. And I think this statement is as valid today as it was 10 years ago. And hopefully I'm going to show you how we can use ice quakes as observations to constrain this friction at the bed. So here are the ice quakes, or the data set we're going to use for this experiment. And it is a data set comprised of roughly 200,000 ice quakes located at the bed of Rutherford Ice Stream in Antarctica. And these ice quakes are shown with these red dots here. Ice flow is 160 degrees from north, so sort of down to the bottom right corner of the screen. I'm not going to talk to you about the method in too much detail, but feel free to come and chat to me offline about the method. But basically what we do is we take ice quakes and we fit a standard earthquake model to the ice quakes and get out a load of fault parameters from the ice quakes. And then we compare those, or put them into a rate and state frictional model and constrain a rate and state frictional model to sort of tease apart what's going on with the friction at the interface between the ice and the bed. And specifically, I think what's important for the ice dynamics model is what is the total shear stress at the bed and what is the slip rate of the bed. And those are the two observations I want to show you today that we get out from the ice quakes. And it's worth noting that in this model, ice quakes can only be generated in an unstable regime. So we're only getting snapshots of this sliding, but we think we're getting snapshots of the entire sliding process during an individual ice quake cluster sequence. So here's observation one, total basal shear stress. And you can see that here's the total basal shear stress versus time for a number of clusters. Each cluster's distinct point in space and is colored by a separate colored line. And we can see that we have a variation of sort of 4 orders of magnitude in the total shear stress. And some of these shear stresses are pretty high, but it's worth remembering that these are acting over very small sticky spots of the order of 10 to 60 meters diameter. So very small spots accommodating a large amount of the total shear stress at the bed. And you can see that they're possibly modulated by tides in some cases, but not in others. And we potentially have a bimodal distribution, which I won't talk about now, but yeah, feel free to ask me offline again about this bimodal distribution and what I think it means. The second observation we have is slip rate. If you remember earlier, I was saying, we have a ice can move via deformation of the ice column or slip. If our ice is moving predominantly by slip, we expect our ice quakes to have slip rates, our ice quake to ice slip rates to be of similar magnitude to the Rutherford mean surface velocity, which is this dashed line here. And indeed, within the uncertainty, a lot of these clusters are within this dashed line, although the uncertainties are quite large. So we have a lot of agreement between the ice quake observed slip rates and the Rutherford mean surface slip rate. So the ice of the bed, there's pretty much no deformation in the ice column. However, there are a few clusters that don't obey this trend. These clusters are probably okay still. They're probably just where you've got a lot of resistance, frictional resistance to the bed, and the ice is temporarily held up for the order of hours to maybe a day or two, potentially, by the friction of the bed. The final result I wanted to show you was these two parameters, variation spatially. I ignore the fault radius, so we can get that out as well. And you can just see that the total shear stresses are highest at the furthest upstream clusters where the ice first hits a kind of hummocky moraine underneath the bed. And slip rates are predominantly uniform across this, which is what we expect because the ice is broadly slipping at the same rate. So hopefully I've shown you that we can really start to constrain basal drag using observations. And we can do that using observations of basal shear stress and sliding velocity derived from 200,000 ice quakes in roughly 1,000 clusters at the bed. So yeah, thank you for listening.
You. The next speaker is Samuel Kachik, Damage Control, Forming Stable Ice Shelves and Simulations with Damage Mechanics.
Hi everyone, I'm Sam Kachuk, a postdoc at the University of Michigan, working on models of calving mechanics and solid earth deformation. Since it's right before dinner now, I'm going to use this time to motivate a series of questions about calving that I've been thinking about, and look forward to discussing them with you before dinner tomorrow. Ice is solid, so it fractures. Ice is fluid, so it flows, and the fractures flow with it, and extend, and join up with other or new fractures. Occasionally, enough fractures coalesce and the ice disconnects, as shown here happening at Pine Island Glacier. How can we represent this small-scale process that can go very fast and depend crucially on minute details of the ice and its history in our large-scale ice sheet simulations? I find that when we try to incorporate macroscopic models of fractures, we end up with catastrophic behavior, or we don't get calving at all. So can we do it? Before we get to that question, a little background. We often represent ice as a continuum, so it's understandable to want a representation of fracture as a continuum process, shown here in traditional volume element form, giving rise to a group of loosely affiliated models under the heading of damage. To focus on just a scalar field variety, we need to imagine the fractures are orientationless, little penny fractures. This allows a handy geometric interpretation of damage as an effective area over which the continuum equations apply. But how to define such a field? Is it the result of an inversion, the factor that allows temperatures, sliding coefficients, and velocities to match up? Is it a density field, representing a continuum of states of ice between intact and broken, taking values between 0 and 1? More macroscopically, can we treat it as the ratio within a volume element of crevasse depth to thickness? Most, if not all, of these models link damage to stresses in the ice and environmental conditions, such as basal melting. Now, we might imagine then that how much the ice is damaged affects how it flows. The traditional flow law for damaged ice multiplies the viscosity by the level of undamagedness, the fraction of the gray intact area to the total face area. The implication is that the holes in the ice are filled with stuff that has the density of ice, but is otherwise inviscid. So we could also apply the damage to the hydrostatic balance to fill the voids with water or fern or air. A still other approach is to imagine the damage doesn't affect the rheology until it does, by causing a calving event that transports the failed ice far from our ice of interest. In fact, as we'll see, these aren't the only options, an idea that might offer a way forward. Let's allow damage to evolve without affecting the ice dynamics, taking, for example, an idealized floating ice shelf with the approximate scale and influx as the Amory ice shelf. Our idealization takes the shelf to be a rectangular block within no-slip walls, and the influx from the left and melting from underneath. These white contours show how this scale matches up to the observed grounded margin and terminus. The purple shows the damage, which increases to the front until the ice is fully damaged. Crevasses reach through the entire thickness, as shown in this hatched region. This model captures the approximate extent of the observed ice shelf. But we run into problems when we allow the damage to affect the viscosity of the ice, as we discussed a minute ago. All of a sudden, the ice disintegrates. The stress along the wall causes damage to increase and make the ice inviscid from the outside in, which is not, I think, what we observe at Amory. We're not alone in seeing this. Take, for instance, these figures of the MISMIP Plus experiments from Sun et al. 2017, with another model of damage. Either the floating ice disconnects from the walls, the cyan contours show areas of thin ice, and flows way out, or enhanced damage driven by melt causes the floating ice to disintegrate way back to a retreating grounding line. So we try something else, more discrete calving. When we periodically remove any ice with crevasses that reach through the full thickness, where damage is 1, the ice disconnects from the wall and it becomes a tongue again. Would it be okay to consider these two end members of a theoretical coupling function between damage and rheology? The traditional effective stress coupling is a linear viscosity multiplier, shown here, and the calving is like a heaviside function making ice inviscid and flowing away instantaneously once the damage hits a particular threshold? If so, can we justify any old coupling function that lies in between them, like this one? What happens? I tried this one and we got almost rift-like localized behavior emanating from the wall where the ice starts to thin. Does this indicate the importance of weakened but not absent ice, like a melange? What could this tell us about the history of the front-initiating rifts we observe at Amory? Returning to Pine Island, we observe floating ice shelves, and these provide a crucial control on the rate of grounded ice reaching the ocean. The effect of damage on the ice's rheology, hydrostatic driving stress, its interaction with ocean and atmosphere and subglacial surface are all potential drivers for ice shelf stability and instability, and I'm looking forward to hearing your thoughts on it tomorrow. Thank you.
Thank you. Our next poster is from Colin Meyer, a thermomechanical model for subglacial frozen fringe.
Hello, everyone. My name is Colin Meyer, and I'm an assistant professor in the Thayer School of Engineering at Dartmouth College. And today I'm going to talk about subglacial frozen fringe. So here I am in a channel in the Mendenhall Glacier, and this photo was taken by Kaya Riverman. And I'm picking at the ice axe this frozen fringe region, this frozen sediments that's within the subglacial channel below the ice. And inside the glacier, and the sediment here is frozen, so the ice continues, inside the sediment below it, and this is what's known as a frozen fringe. And these frozen fringes, they show up under mini glaciers. So in the upper left, here's Taylor Glacier. On the right here is a borehole image taken from the Whillans ice stream, and it shows that they show up here, these frozen fringes in lab experiments as well, and they play a crucial role of describing the interaction between the ice and the sediments, basically the thermomechanics of the sliding interface at the bed of glaciers and ice stream. And they play an important role in setting the friction through fast flowing glaciers. And so what we can say is that the ice is this solid phase, and there's if there's some sort of interface between the water and sediments and the ice, then there's a distinct melting temperature. But if there's a frozen fringe, then there's a mushy zone between the solid phase and the water and sediments, and that is that frozen fringe. And that the saturation, the partial saturation, so there's water, ice, and sediment, and that saturation, the ice saturation, is a function of the temperature below the melting temperature. And that's shown here as an affine power law. And if we plot this in enthalpy space, where we say, okay, the enthalpy, the difference between the pure ice and the water and sediments, well, that would be the latent heat. And if we say that there is this mushy zone, this frozen fringe, then it sort of maps between the water and sediments and the pure ice, smoothing out that transition. And so what that allows us to do is in a single computational domain, write out the ice lens, the frozen fringe, and the water and sediment just by solving for the enthalpy for all three of these regions. And when we do that, we can find steady states for the frozen fringe thickness, for glaciological parameters for the effective pressure, and then this is here, the V is the melt rate or the freezing rate, and so we can figure out where steady states exist and where transients exist. And so here's a steady state for V equals 0, so for balanced thermodynamics, and an effective pressure plotted along the bottom, and then fringe thickness in meters. And so this, as the effective pressure becomes a large multiple of the infiltration pressure, the pressure required for the ice to infiltrate into the sediment, we find that we can get sort of meter scale frozen fringe regions. Now in freezing regimes, what we have is that we can actually generate ice lenses inside the frozen fringe. So as the frozen fringe is sort of like drawing in water and freezing from the bottom, the effective pressure, the local effective pressure can become very, very small within the frozen fringe, so small that it can basically hydrofracture and lead to ice lenses forming inside the fringe. And so basically what happens is that the local effective pressure goes to 0, we move the domain up, we run the simulation again, and then the local effective pressure goes to 0, we move the domain up, we run the simulation again, and so on and so forth. And we can get a sequence of ice lenses. And so schematically, what this shows is here in the porosity, we can find we have ice and then water and sediments below, and then we get a fringe. We form an incipient ice lens. We move the domain up. Then we have ice, fringe, and then a new ice lens forms. And then yada yada yada. We get the sequence of ice lenses forming. And this is reminiscent of the experiments from Tabor and some nice theoretical work by Fowler and Noon. And so the important piece of what we've done with with our enthalpy simulations is to map out a phase diagram of N, the effective pressure, and V here, which is the melt rate, I guess it's the freezing rate. V is the freezing rate. And so for positive freezing rates, what we can get are these periodic lenses, and we can also get steady lenses for very small freezing rates and small effective pressures. And then for negative freezing rates, for melting rates, we get the steady lenses with a fringe. So this is that steady state that I showed in the beginning. So what we've talked about is a little bit about frozen fringes and pre-melting. We did enthalpy fringes in one dimension, and we showed ice lenses and their periodicity, where we can find a steady fringe in the case where we have net melting or very small freezing and low effective pressures. And then also, if we have net freezing, we can get this periodic banded structure of ice lenses. So thank you very much, and feel free to send me an email if you have questions, and I'll look for seeing your talks online. Cheers.
Thank you. Next up, we have David Michalak, the Antarctic Meteorological Research and Data Center.
Hello, I'm Dave Michalak, and I work at the Antarctic Meteorological Research and Data Center at the University of Wisconsin-Madison. And today I'll be going over what the AMRDC is. So the AMRDC aims to bring Antarctic meteorological data sets to the broader community with an emphasis on observational data sets. So the AMRDC is essentially an extension of the pre-existing Antarctic Meteorological Research Center that was established here at UW-Madison back in the early 90s. And so the AMRDC, the goal of this project is to become an official data repository for Antarctic meteorological campaign data sets. The goal of the previous AMRC was to house any and all Antarctic meteorological data, and the AMRDC hopes to continue that mission. So some of the data products that are involved in the AMRDC are Antarctic meteorological campaign data, and that's both from the UW-Madison's automatic weather station program and any field work that we would do, as well as any other science groups Antarctic meteorological campaign data. The AMRDC will also continue to provide real-time automatic weather station data, both from the UW-Madison group and any other international groups. And the AMRDC will continue to create Antarctic satellite composite imagery. A couple examples are shown there. That's of infrared data. The satellite composite imagery will include 5 channels: infrared, long wave, short wave, water vapor, and visible. So some of the people involved in this project include personnel such as staff and students from UW-Madison and Madison Area Technical College. And these people are involved in every aspect of the generation of the AMRDC project, including server development, setting up the repository server, the web server, as well as the satellite composite generation servers, to creating the repository website framework, to creating the AMRDC website. And also the students are in particular working on climatology reports for certain automatic weather station locations. The AMRDC Advisory Board is also another group of people who are gathering input so the AMRDC is gathering input from this advisory board to get advice on data infrastructure, operational needs, and student and early career scientist perspectives. So we want to make sure that the AMRDC is an all-encompassing project, and we want to make sure it works for everyone. So the figure in the middle there shows in the green the different servers that are involved in setting up the AMRDC, and the blue clouds, I guess, are the different types of data that will be created and or offered through the different servers, and that shows how it's kind of all connected. So the AMRDC deals with a lot of data and how will it be made available. The biggest one that our goal is to have the data repository, which is now open. It has the URL is listed there at the top of the poster. And so this repository will provide Antarctic meteorological data archive, metadata on the data, and digital object identifiers for any campaign data sets that are submitted. And the goal of the repository is to follow the FAIR data principles. And so the data will be findable, accessible, interoperable, and reusable. Another way the data is provided is with meteorological data distribution. And so that's focused on real-time data flow, utilizing servers such as with Michalak, ADDE, and we're working on threads right now, and also with services such as the Antarctic Internet Data Distribution via LDM, which is Local Data Manager. And the figure on the bottom there shows kind of how the Antarctic IDDE or IDD system is set up with the different locations like Wisconsin and places in Colorado down to places in Antarctica, and how data flows between the different sites. There will be a new website coming soon, and so be looking for that in the future. Thank you very much.
Thank you. Our next speaker is a student, so please provide feedback. Helen Allen, Inverting Ice Surface Elevation and Velocity for Bed Topography Beneath Thwaites Glacier.
Hi everyone, I'm going to be talking about inverting ice surface elevation and velocity for bed topography beneath Thwaites Glacier, West Antarctica. I'd like to thank my collaborators from the University of Edinburgh, and I'd also like to say that our preprint paper on this topic is currently available on the Cryosphere website. You can either follow the link at the QR code in the top left-hand corner or just find it yourself. So, why are we interested in the bed beneath Thwaites Glacier? Well, like many marine terminating glaciers in West Antarctica, the bed beneath Thwaites Glacier gets deeper as you go inland, and this means it's vulnerable to the marine ice sheet instability. Not only this, but smoother versions of the same bed topography give significantly different retreat rates in models, meaning that not only do we need to know the broad-scale topography, but we also need to know what's happening on the smaller scales. What do we do if there's no bed data? Well, as part of the International Thwaites Glacier GHOST collaboration, hopefully we'll be collecting a variety of geophysical data across Thwaites Glacier. However, in the meantime, I've been looking at what the surface can tell us about the bed. Where we have these high-resolution swath radar patches, we can see that landforms in the bed often show a startling resemblance to the much subtler landforms in the surface of the ice above them. Luckily, there's a mathematical relationship which describes this relationship between the bed and the surface, developed by Hilmar Gudmundsson and based on the shallow ice stream equations. We've been using a least squares inversion version of this mathematical theory, which allows us to take the ice surface and say what we expect the bed to look like. I'm not going to go into the details of this methodology in this talk, but just to say that with synthetic tests, we can resolve landforms with an angle to flow of greater than 15 degrees and bed features that are greater than 10 meters in amplitude and greater than 2 kilometers in wavelength, where 2 kilometers is the ice thickness. We've been applying this inversion to the REMA surface elevation data and its live velocity data over a region of the central trunk of Thwaites Glacier. As a result of this inversion, we have two key results: a new bed topography map for Thwaites Glacier and associated bed slipperiness product, and both of these also have standard deviations. I'm mainly going to be talking about the bed topography product today, but I'll briefly mention bed slipperiness at the end. We can compare the bed topography product from the inversion to existing radar data, including these two swath radar patches from Holshue. We can see in the upper Thwaites patch that the inversion picks up the location of all the key hills very well, and we even can see the outline of this potential subglacial meltwater channel, which is very encouraging. In the lower Thwaites radar patch at the bottom, we can see that once again the inversion picks up the location of the key hills well, but the amplitude of the topography in between these hills isn't always correct. Comparing to bed machine, we can see lots of similarities between the inverted bed topography and bed machine, including in the regions where those two swath radar patches have been included. However, there are also plenty of other regions where we see quite a big difference between the topography inverted by this inversion and bed machine, including this region of selection of parallel ridges close to the eastern shear margin. Comparing to airborne radar lines shows us that in fact this region of parallel ridges near the eastern shear margin is shown in airborne radar data and not in bed machine, which suggests that this inversion is picking out real features which are there. However, before you get too excited, I should also point out that often comparing to radar lines shows that this inversion topography is often much higher in amplitude than we would expect. Why could the amplitude be wrong? Well, we think this is due to the trade-off between the topography and the mean slipperiness parameter C, which we impose in the inversion. Increasing this mean slipperiness parameter decreases the amplitude of the topography, but crucially, it doesn't change the pattern that we see in the topography, meaning that even if the amplitude is wrong, we think that the location of the hills and troughs that we pick up is meaningful. Unfortunately, there's no ideal single value of C, the mean slipperiness, and you can see here that for this swath radar patch, we think that the slipperiness of 100 is better, whereas for this radar line, we think a slipperiness of 150 is better. And we think this could potentially be because C, the mean slipperiness, is variable across the Thwaites Glacier catchment, whereas we've just imposed a single value. And all this means that we, once again, aren't entirely sure on the amplitude of our bed slipperiness product that we produce, but we think that the pattern we see here probably is meaningful, and hopefully it can be used in models or in comparing seismic products in the future. So to conclude, this inversion gives a reasonable match to radar data considering the lack of prior knowledge used, but there are some problems with the amplitude of landforms, which I think is due to trade-off between slipperiness and topography. Further work on this inversion includes applying this technique to other areas of Antarctica where there are fewer radar flight lines and using a more complex version of the transfer functions from Goodman's in 2003. Thank you very much.
Thank you. Thank you. Our next speaker is also a student, so please provide feedback. We have Andrew Pretorius, application of machine learning methods to identify glacial seismicity in a distributed acoustic sensing dataset from Store Glacier, West Greenland.
Hi, I'm Andrew Pretorius, and I'm about to finish the first year of my PhD at the University of Leeds, and I'll be talking about my research project, which looks at applications of machine learning to identify glacial seismicity in a distributed acoustic sensing dataset from Store Glacier, Greenland. So, why is this useful? What's the point? The point of this research is to develop an automated process to detect seismicity via machine learning, which will decrease the time required for a researcher to analyze large datasets. Overall, the research aims to catalog cryoseismicity within Store Glacier and analyze properties such as ice crystal orientation fabric, ice temperature, and basal conditions. We'll get back to the machine learning in a minute, as I'd like to start by talking a little bit about the site where the data was acquired and how it was acquired. This research uses data that was collected in July 2019 for the Responder project, which is a collaboration between groups shown in the previous slide, and it was collected on Store Glacier, West Greenland, which is a fast-flowing outlet of the Greenland ice sheet. The survey consisted of a distributed acoustic sensing system deployed within a 1,043-meter deep borehole, and it was actually the first borehole glaciological deployment of a distributed acoustic sensing system. Both active source and passive records were collected, and the data was acquired with a 10-meter gauge length and 4 kHz sampling rate. So, just in case anyone is unfamiliar with distributed acoustic sensing, or DAS, it is a relatively new technology that uses a fiber optic cable itself as a pseudo-seismic receiver. So what this means is that changes in strain in the optical fiber caused by an acoustic field, in this case a passing seismic wave, create a phase lag in the backscattered pulses of light as they travel through the cable, and this phase lag is used by what's called an interrogator unit to then recreate the seismic signal. This effectively turns the cable into a very densely sampled string of geophones. The strain on the cable is averaged over a predefined length, known as the gauge length, which gives the effective spatial resolution of the cable, as wavelengths shorter than this cannot be detected. However, the signal is recreated with pseudo-samples every meter, which use this average seismic response from within a 10-meter wide, the gauge length, window in which the pseudo-sample is centered. So DAS is able to produce a high resolution vertical seismic profile, or VSP. Here we see some examples of data that was collected with this DAS system on Store Glacier. At the top, we have examples of cryoseismicity seen within the passive recording. You can see a P wave, an S wave, and some reflections from the surface. And then underneath, there is an example from the active shot, in which we can also see a P wave, a basal reflection, and another S wave. So DAS produces these 2D images at a good resolution for seismic data, and the passive recording from which the example at the top is taken is 3 days long, and that produces a very large quantity of data. This is cumbersome and time-consuming to analyze, and the process of this manual identification of events could create a bottleneck in the data analysis process. So there is potential for a more efficient way of doing this, and this is where machine learning comes in. So we have this data that is essentially just a 2D image. So I decided to look at image recognition algorithms for the task of automated event detection. A convolutional neural network is a deep learning algorithm that uses convolutional filters on any sort of 2D array and is able to detect the spatial relationship between the data samples within that array, i.e. the pixels within an image or each sample in a time series. This allows the convolutional neural network to recognize features within the image. The method I used was to take high signal to noise ratio active shots and to take windows from within the data and basically just train the algorithm to detect whether this window contains coherent seismic energy or not. The method this uses scans across the data with a rolling window, as shown by the animation playing now, and will highlight where it does detect coherent seismic energy. This shows a lot of promise, as the convolutional neural network can successfully identify windows containing coherent energy from primary PNS wave arrivals, with a high accuracy of around 90% in tests. So that means 9 out of 10 windows were correctly identified as containing coherent energy or noise. The algorithm output can be considered a score, essentially saying how certain it is, with a score of 1 being absolutely certain and 0 being completely random noise. Following from these initial tests with the active shots, this approach is now being tested using the passive recording, with the hope that after optimization, the CNN will be able to successfully identify coherent arrivals in the passive data. So, back to where we started. Why is this useful? As I mentioned previously, the aim is to develop a process using this algorithm that is able to save the user time compared with the manual appraisal of very large passive datasets. These initial results demonstrate the capabilities of a convolutional neural network for this purpose, and hope to soon develop this into a fully automated process which is able to identify cryoseismicity accurately. Thank you for listening.
Thank you. Next, we have David Pryor, Flow Laws for Ice Sheet Modeling. Sorry, experiments tell us that n approximates 4, not 3. And let me rename the speaker since you probably didn't hear. It's David Pryor.
Kia ora. I'm Dave Pryor from University of Otago in New Zealand. I'd like to share some thoughts with you about the stress exponent for ice deformation flow laws from an experimentalist point of view. Glenn himself started the ball rolling. He pointed out that the values of 3 and a bit from his experiments only applied to the minimum strain rate in experiments, that small strain. In all his papers, he argues that higher strains, steady state, tertiary creep, n should be about 4, and he was right. The n value is important. Here's the outcome of 2 different models for Greenland, n equals 4 from Bons et al., n equals 3 from McGregor et al. Blue is frozen base, red is not frozen base. You can see the model outcomes are very, very different from each other. The empirical base for n equals 4 is really strong. Every experiment which has enough data to define a tertiary creep n value has a value of 4, or in some cases rather larger than 4. Okay, so there's a constant load experiments, constant rate experiments, a whole range of temperatures. Durham et al. 1983 defines a flow law for ice, which has an n equals 4 value. This is a summary plot of some of the data, and you can see n equals 3 really does not fit. N equals 4 does fit the data. So let's unpick a little bit where n equals 3 comes from. The Glenn flow law uses data from very low strain, what's called the minimum strain rate or secondary creep. The equivalent in a constant rate experiment would be the peak stress. And that's important because the grain size hasn't changed from the starting grain size. The total strain rate in any crystalline material will be the contribution of all the strain rates to all the different mechanisms which are operating. And in ice, there are grain size insensitive mechanisms, dislocation creep, and grain size sensitive mechanisms, such as grain boundary sliding, and they both contribute. So the n value that you measure in any experiment will depend upon the stress and the grain size of that experiment. Here's a map showing different n values from a calculation from flow laws, and some experiments plotted on there showing practical n values that have been gotten for particular experiments as a function of grain size and stress. And you can see they're quite variable. And the n equals 3 happens to be from experiments which are easy to get grain sizes, easy to get strain rates. That's a critical thing, which corresponds to stresses. But the n equals 3 cannot be scaled. You can't scale it without having a grain size relationship. So it's meaningless. On the other hand, when you get to tertiary creep, the grain size has evolved. And so the mechanics, the rheology changes because the grain size gets smaller, but the grain size you get actually depends on the stress. So here are some points for grain size at tertiary creep as a function of stress. There's grain size axis, stress axis, and they lie on a line, which happens to be the line for equal rate the two mechanisms. Because of that, the math simplifies. Okay, the equation that governs the strain rate is the sum of the strain rate of the two mechanisms. On that boundary line, the strain rate of those two mechanisms are equal. So we can simplify those to say that the total strain rate on the boundary line, where the data lie because of the microstructural evolution, will be twice the insensitive strain rate, and it's only dependent on the stress exponent for the insensitive creep mechanism, n equals 4. So we have an explanation for that. Summary. Okay, if you're modeling ice at high strain, that includes basal ice, shear margins, general flow, most ice sheet models, don't use n equals 3. It's wrong. Use n equals 4. There's a good empirical database for that. If you're doing anything more sophisticated, like looking at situations where microstructure changes, sudden changes in kinematics, tidal flexure, etc., you need a more sophisticated flow law, a composite flow law that includes grain size sensitivity and fabric sensitivity. I'll be very happy to discuss this with anyone. I should be appearing on Zoom, so hopefully that's possible. If not, you can email me or set up a meeting. It's something I'm quite passionate that we get right in the models because it's not right at the moment. Thank you very much.
Thank you. Next, we have Brittany Schmidt, ice loss from asymmetric melting at Thwaites Glacier grounding zone.
Hello, my name is Peter Washam. I am a research associate at Cornell University. I apologize if my introduction's a bit repetitive, but I have multiple talks. I'm not sure what order they'll be in. So yeah, I work in Brittany Schmidt's group, and we recently moved from Georgia Tech to Cornell. And I'm going to give a talk on some of the work that Brittany is leading on results from some field work that was conducted at the grounding zone of Thwaites Eastern Ice Shelf. So this map shows the Eastern Ice Shelf of Thwaites, and this blue shaded region is the collection of grounding lines mapped between 2016 and 2017. So in January of 2020, a field team deployed to this region, and the British Antarctic Survey drilled a borehole right here. And then Brittany and her team took the hybrid autonomous remotely operated vehicle IceFin through that borehole and collected these 2 transects beneath the ice shelf over 5 separate dives. And here are the results from those dives shown in 2 dimensions of the ice, the ocean, colored by temperature over freezing or thermal driving, and then the seafloor in brown. And what you see here, T1 is this almost 3 kilometer long transect, which is that burgundy line here. And then T2 is this 1,600 meter long transect shown here on the right. And what's very exciting about this one is that they actually map the ice, ocean, and seafloor all the way to the grounding line point. And some key takeaways from these figures is that the ice is sort of very irregular, and as you move away from the grounding line, it sort of lowers in the water column. The seafloor is moving up towards the grounding line, so we would call that a prograde bed slope. When we think about grounding line retreat, that is at least. And there's these 2 very large crevasses, or sorry, 3 very large crevasses in each of these profiles. And then as you move away from the grounding line, there's the ice base flattens, and then there's these really nice terraces that we see. And the water column is very warm at depth, and it cools with proximity to the ice base. And these stars show past grounding lines mapped within SAR that we cross. So the white is that 2011 grounding line, and then the blue is the outer edge of this 2016 grounding line. And here's the data shown in salinity. So the water also freshened due to melt input. So what we did is we took the temperature and salinity as well as the current speed, which I didn't show, and we looked at it spatially and identified basically 4 regions or 5 regions, because some of this data was in a crevasse, where the data exhibited a certain characteristic. And so we took those temperatures and salinities shown here and multiplied them by the current speed and our best guess of what the boundary salinity was and temperature was at the ice-ocean boundary. And we used them to compute a melt rate using the 3-equation melt parameterization of Holland and Jenkins, and tuned all of that to an AP-Res observation right here. So basically the computed melt rates along sort of the flat outer portion of T1 right here had to match that AP-Res long-term mean melt rate. And basically I don't have time to go into all the details of these melt rate calculations, but basically the takeaway here is that anything with a steep slope is going to melt faster, and it's going to melt kind of like laterally instead of upwards, instead of when compared to sort of these flat ice base. And that's because the stratification of meltwater basically stabilizes the boundary layer and suppresses melting along flat portions of the ice base. But then along these sloping regions, it does not suppress melting, so you'll have higher melt rates. And that's what we're seeing here, is basically anything with a slope can melt laterally a good deal faster than anything with a flat slope can melt vertically. And then the question is really just what's the ratio of these slopes along the ice base. So thank you for your time. Here are my acknowledgements. Goodbye.
Thank you. Next, we have Olga Sergiento, Stability of Marine Ice Sheets in the Presence of Feedbacks.
This study investigates the effects of surface elevation feedback on stability of grounding lines of marine ice sheets. It is well known that the surface temperature is a strong function of surface elevation. The top plots show the surface temperature computed using a regional climate model MAR for Antarctica on the left and Greenland on the right. The highest temperature is at the margins of these ice sheets, where the surface elevation is the lowest, and the temperature progressively decreases towards the interior, where the surface elevation is the highest. Bottom plots show the accumulation ablation rates for computed in the simulations. Accumulation rate increases and ablation rate decreases. That is, it becomes more negative as temperature increases. All existing studies of marine ice sheet stabilities treat accumulation ablation rate as a function of horizontal coordinate only and keep it constant. They also disregard any feedbacks that might be present in the system. This study constructs a relationship between accumulation ablation rate, surface temperature, and surface elevation, and it investigates stability conditions of steady-state marine ice sheet, which experiences feedbacks between the surface elevation temperature and the accumulation ablation rate. In order to construct an empirical relationship between accumulation ablation rate and the surface temperature, MAR simulations for Antarctica and Greenland has been used. These simulations were done for RCP 8.5 scenario in order to increase the range of the surface temperatures. The blue dots on this plot are Antarctic simulations and green ones. Greenland simulations, the green line is a fit and shows the empirical relationship between the surface temperature and accumulation ablation rate. This surface temperature is a function of the surface elevation. It decreases in accordance with the lapse rate. Using this empirical relationship, an idealized configuration of marine ice sheet has been computed. It is shown on the top plot, the steady-state ground line position on the upsloping bed. The bottom plot shows the accumulation ablation rate as a function of distance from the ice divide. This is the plot on the bottom left as a function of the surface elevation. This is the plot on the bottom right. In order to evaluate the stability of this ground line position, it has been perturbed from the steady state shown by the dashed line on this plot. The plot on the left shows the evolution of the ground line position in the accumulation ablation rate varies with the surface temperature, and the surface elevation is apparent. In this case, the grounding line is unstable. The plot on the right shows the evolution of the grounding line in the accumulation ablation rate is treated as a function of the spatial coordinate only, and as apparent from this plot, the grounding line is stable. Stability of the grounding line is different if feedbacks are accounted for or not accounted for. In the presence of feedbacks, the grounding line is unstable, and in the absence of feedbacks, the grounding line is stable, at least in this particular example. A linear stability analysis shows that in the presence of feedbacks, there is no general stability condition similar to one of marine ice sheet instability. And stability conditions can be determined only on a case-by-case basis for individual configurations of marine ice sheets. These results also apply to other feedbacks, for instance, subice melting that depends on the thickness, glaciostatic adjustments that depends on the sheet mass, erosion and sedimentation processes, and also changes in the local sea level. The direct empirical relationship uses the fundamental relationships between the atmospheric surface temperature and precipitation and the surface temperature and the sheet surface melting. This expression can be an efficient tool for paleoclimate simulations. Thank you very much for listening. I'll be happy to answer your questions.
Thank you. Thank you. Our next speaker is Paul Summers. They are a student as well, but also giving a talk tomorrow, so I might suggest we wait to give feedback until we see the talk tomorrow. They will be presenting evidence for temperate ice in shear margins of Antarctic ice streams from airborne radar surveys.
Hello, my name is Paul Summers, and today I'll be presenting evidence for temperate ice in shear margins of Antarctic ice streams from airborne radar surveys. The majority of ice loss from Antarctica flows through a system of narrow, rapidly sliding regions called ice streams and outlet glaciers. These regions are laterally bounded by areas of intense shear strain and are named shear margins. In these regions, intense friction from the shear strain drives in glacial heating and in some cases even produces pockets of temperate ice. Meyer et al. 2018 developed a thermomechanical 1D free boundary model to infer which Antarctic shear margins may contain temperate ice. Building off of this, we extend their model of ice temperature to a model of glacial radar attenuation as a function of depth for any position on the continent. We then apply this attenuation model to existing airborne radar surveys. Specifically, we consider flight lines over several high strain rate shear margins and the degree to which dips in bed echo power can be explained by an increase in glacial attenuation due to shear heating. To this end, we construct two glacial attenuation models for Antarctica. One model uses only the Robin thermal model for attenuation and neglects shear strain heating effects. The second attenuation model uses the Meyer thermal model to include shear strain heating effects on expected glacial attenuation. We use these attenuation maps to compare observed dips in bed echo power across Antarctic shear margins to the expected increases in glacial attenuation due to warm or temperate ice, and the degree to which shear strain heating contributes to these warm pockets in Antarctic shear margins. Shown here on the right is an example flight line from the Cycle coast. In the upper left, we have the radargram with the bed and surface pics plotted in red and blue. In the upper right, we have a map view of this flight line where the star is the start of the flight line. And this is on top of a color plot of surface speeds and a logarithmic scale. We also have the modeled temperature profile for this cross-section as a function of depth and distance along flight line, where this model here is our Meyer model that does include shear strain heating effects. For our plots of bed echo power, we have a simply range-corrected bed echo power here with those bed echo powers in red, where the dashed line is the moving mean for this slightly noisy bed signal. And in the lower left, we have the bed echo powers when they've been both range-corrected and have an glacial attenuation correction factor, but that correction factor is only the Robin correction and is not including any shear strain heating effects. We also plot the expected attenuation that we would see when we include shear strain heating effects, or the Meyer model, with this blue dashed line shown here, which predicts a significant dip in bed echo power around the 500 mark of this particular flight line. And when we look at the observed bed echo powers, again in red, we see that there is a match in location for observed dimming of the bed echo power at the shear margin itself, but the exact magnitude of this dimming is not fully consistent with the predictions from our thermal model.
We then take this methodology and apply it to three other shear margins in Western Antarctica. Shown here in the lower left is our example from the Cycle coast again, shown for completeness. When we move slightly farther grid north to Institute Ice Stream, we see a similar result where the predicted dimming by the Meyer model is in the same location and has a similar shape to the observed dimming of the bed at that shear margin, but that the predicted attenuation and glacial attenuation is a little bit of a larger magnitude than the actual dimming we observe of the bed. Moving slightly grid north again, we go to Recovery Ice Stream, where the bed actually dims out of recognition and is lost inside of the shear margin. We see this dimming of the bed to beneath the noise floor as consistent with the hypothesis of there being a temperate shear margin in this location, because the glacial attenuation that would result from the presence of a temperate shear margin would produce enough glacial attenuation to bring that bed echo beneath the noise floor. Moving to our final location of Pine Island, we see that in this case, the significant glacial attenuation predicted by the Meyer model is not reproduced either in location or general shape of the observed bed echoes for this flight line. We think that this discrepancy may be due to the fact that there's significant amounts of lateral advection of cold ice in this region, which is not included in the Meyer model and would serve to reduce the intensity of any temperate pockets in this region.
Thank you. All right, everyone, we're in the final stretch. We've got 3 left. Thank you for sticking in there. Okay, next up we have Peter Washam, a synthesis of ice-ocean interface observations from the underwater vehicle ice fin.
Okay, hi everyone. My name's Sandy Thompson. I am a physical oceanographer at Caltech, and I'm going to be talking today about some of the work that we have done as part of the Tabasco project, which is funded by NSF. And I really just want to give an overview of some of the work and hopefully encourage people to look at some of the publications that have come out of this and work in progress. And it sort of falls under this umbrella of the 3-dimensional circulation of the West Antarctic shelf seas. And I've listed my co-authors down below. So if I
Hello, my name is Peter Washam. I'm a research associate at Cornell University. I recently moved there from Georgia Tech, and I'm not going to give the talk that's listed in the agenda today because it's impossible to give in 5 minutes. So instead, I'm going to share some recent results entitled Observations of 3-Dimensional Ocean Circulation in an Ice Shelf Crevasse and Implications for Melting and Freezing Rates. So the data was collected in 2019 to 2020 at the back of the Ross Ice Shelf near the Cam Ice Stream grounding zone. So a team of dedicated hot water drillers drilled through the ice shelf here, and then a group of us took the hybrid autonomous remotely operated vehicle ICEN and deployed it through the borehole and collected this track beneath the ice shelf. So it's colored here by ice base elevation, where blue is low and white is high. And you can see there's these 4 crevasses here. And we took the vehicle into this crevasse right here, outlined in red, and collected some very detailed observations. So here's a 2D view of the crevasse. So gray is ice, blue is ocean. Brown is seafloor, so the crevasse is about 50 meters wide and 50 meters tall. It's split into 2 sections here, where the blue is the vehicle track on this east side or left side of the crevasse, and the red is the vehicle track on the west or right side of the crevasse, and these white lines mark the supercooling horizon. And so we collected the ice topography on the outbound part of the dive, and then on the return was when we took the vehicle into the crevasse, and you can see there's some misalignment between the vehicle and the ice topography. So we're not actually in the ice at this point. It's just the nature of being in these very sketchy situations with an underwater vehicle. So we collected really nice ADCP data, and I've broken them up here into the V, which is the north-south component, the U, which is the east-west, and then the W, which is the vertical component of the velocity. And you see here the purple data show the strongest flows into the page or southward at about 6 centimeters a second, and then there's the secondary circulation, which is a rising and sinking in the crevasse of about 1 centimeter a second or so. And the strongest sinking, which is up towards the top left side of the crevasse, is also associated with a westward flow. So here's the data shown in a compass. So the west side again being that right side, and then the east side being that left side. And you see indeed the flow is almost dead south in the crevasse on the west side, and on the east side it's a little more jumbled. And when you look at the vertical profiles, the gray lines here mark the crevasse, and then this is the data below. You see that strong southward current associated with a rising of the water up to about 2 meters a second, or centimeters a second almost. And then on the east side, that sinking, which is close to the supercooled horizon, which is shown in white here, that sinking also associated with that westward flow. And when we look at the vertical profiles of the hydrography, now again, the gray lines mark the crevasse. You see here's thermal driving, salinity, buoyancy frequency, speed, and then an estimated melt rate. You see that indeed there's the super cooled water, and that sort of warms with depth. But what's interesting, you see all this interleaving and salinity, which reflects itself in the buoyancy frequency, which shows that the whole water column was unstable. So there's rising and sinking going along in the crevasse. And when you take the speed and the thermal driving and just do a really rudimentary rough estimate of the melt rate, you see the west side, you're getting melt rates of up to about 2.5 meters a year. And then on the east side, you're close to zero and actually negative in places. So here's some acknowledgements. Thank you for your time. Goodbye.
Okay, our next speaker is Andrew Thompson, speaking on the three-dimensional overturning circulation of the West Antarctic shelf seas.
Okay, hi everyone. My name's Andy Thompson. I am a physical oceanographer at Caltech, and I'm going to be talking today about some of the work that we have done as part of the Tabasco project, which is funded by NSF. And I really just want to give an overview of some of the work and hopefully encourage people to look at some of the publications that have come out of this and work in progress. And it sort of falls under this umbrella of the three-dimensional circulation of the West Antarctic shelf seas. And I've listed my co-authors down below. So if I had to summarize what some of the key results are of this study so far, I've listed them here. One is that the export of meltwater influences the frontal structure and the currents at the continental slope. 2, there is a coherent circulation feature that links all of West Antarctica, which is the Antarctic coastal current. 3, coastal dynamics allow for an intersea exchange and impact on ice shelf basal melt rates. And 4, coastal dynamics may be able to induce multiple steady states for the continental shelf overturning circulation. And again, I'm not going to get into the detail of any of these, but I'm just going to have one slide for sort of each of these ideas. The first study that I will show was a publication that came out in 2020, looking at the circulation in the Bellingshausen Sea. And in particular, there is a funneling of glacially modified waters out to the shelf break on the western side of the Bellingshausen Sea. You can see that it's that wedge there of glacially modified winter water that modifies the density structure as shown by the contours there that set up a geostrophic flow. And in particular, there's a westward flow that leaves the Bellingshausen and head towards the Amundsen. The important thing here, though, is that there is a control of the frontal structure. And in particular, we believe the exchange of heat across the shelf break that doesn't depend locally, say, on the wind stress or other properties at the shelf break, but rather there is this connection here between the coast and the continental shelf. And so there's a non-local feedback between melt-driven water modification and heat transport onto the shelf, which ultimately gives rise to that melt. Another exciting result that has come out of this study is that we have used observations collected from instrumented seals to show that the Antarctic coastal current, which is a buoyant freshwater current that's fairly well documented along the western side of the Antarctic Peninsula, that it flows south along the peninsula and continues unabated, and in fact actually strengthens all throughout the Bellingshausen Sea. And so what you're looking at here is a map of surface dynamic height. The contours here would follow the direction of the geostrophic flow. When those contours are closer together, the current is stronger, so you can see it strengthens there in the central Bellingshausen Sea. And that circulation feature may actually flow into the Amundsen, although the pathways by which it does so remain somewhat of an open question. And that's really interesting because it led us to carry out a series of numerical sensitivity experiments where we looked at the impact of melting or freshwater flux that may come from glacial runoff into the Antarctic coastal current along the West Antarctic Peninsula. And what we found is that that perturbation gets propagated, or the signal of it gets propagated westward into the Bellingshausen and into the Amundsen. and it modifies the stratification right in front of the ice shelves, and that changes the partitioning of heat going into the ice shelf cavities, which has an impact on ice shelf melt rates. And what I'm showing in that figure below is the change for all of the ice shelves throughout West Antarctica. That's that bold number WAIS. And we see that the ice shelf melt rate increases by at least 20% due to perturbation. Again, that is not local to the Bellingshausen and the Amundsen Sea, but happens actually up to the northern part of the Antarctic Peninsula. And then you can see for various other ice shelves that are listed there, there are a range of different responses, and some have quite a strong response, such as the Abbott ice shelf, which is shown there, which increases its melt rate by almost 50%. And so that's led us to start spending a little bit more time thinking of the dynamics of what's happening right in front of these ice shelves. And what has motivated this, you see this picture here that comes from that really nice paper by Adrian Jenkins and colleagues in 2018. We know, this is for instance in front of Dotson ice shelf, that we have these years of different regimes where we have thick and thin cold circumpolar deep water layers. These are also coupled to changes in the water structure properties. And in particular, if we look at the stratification, which is shown on the left, they're very different from year to year. So we've been looking at some very simple models that looks at the relative impact of partitioning of the overturning between melt in the ice shelf cavities and convection that happens in polynyas. And there's some preliminary evidence that we can get multiple steady states. And in particular, we can find hysteresis behavior as well. And that's work in progress with Caltech grad student Ruth Morman, who's also attending the meeting this week. So on interannual to multi-decadal timescales, ice shelf melt responds to forcing throughout West Antarctica, and we believe that the impact of coastal freshwater dynamics on the shelf circulation remains underexplored. Thanks to the organizers for what I'm sure will be a great meeting, and thanks for paying attention. Bye.
Thank you. Okay, last and most definitely not least, we have a student presentation by Mariam Zarindarat. Please listen on, she presents stability of surface basal crevasses in marine ice shelves, and please do provide feedback. Thank you.
Hello, I'm here to talk about the stability of surface and basal crevasses on marine ice shelves. Ice shelves at the margin of ice sheets from grounding line to the calving front are usually full of crevasses both on surface and base of the shelf. Here we want to study ice calving and in general propagation and the stability of these crevasses. So why iceberg calving? As you know, ice calving has gotten a lot of media attention, and probably you heard many breaking news about extreme calving events. Also, calving is the main component of mass loss in both glaciers and ice sheets. Increase in rate of calving results in glacial acceleration, thinning, and shrinking, and calving is the largest uncertainties in ice sheet models. Many people worked on calving in the past few decades and used different methods like zero stress theory, statistical models, discrete element method, continuum damage mechanics, or linear elastic fracture mechanics. But all of them have some gaps, like they are limited to the specific geometry, or they cannot estimate the crack length, or they are ignoring some physics like hydrofracturing or interaction between the cracks, or they are computationally so expensive, so not feasible for large scale models. Here, our plan is to fill these gaps. So use linear elastic fracture mechanics to answer how far cracks propagate into the ice, and in which situation does a crack fully propagate through the thickness, and what are the fundamental parameters that affect the stability of the crack. Our geometry is a small part of a shelf that can have one crack at the surface, one at the base, or two aligned crack at the same time. The hydraulic condition can be having a constant water volume inside the top crack, or the water level below the surface being constant. As a propagation criterion, we are using a stress intensity factor that shows the concentration of stress at the crack tip. By comparing these to the fracture toughness, that is a material parameter for the ice, we can decide whether a crack grows or remains stationary. After doing some analysis and scaling, we reached to the fact that there are three main groups of parameters that controls the behavior of the system: scaled extensional stress, scaled water volume or water level, and scaled fracture toughness that is related to the thickness of the shell. We solved this model numerically using boundary element method. As an example of our result, this is what we get for the diagram of stability of a single surface crack with a constant water level inside it. This plot shows the relation between three main groups of parameters. So water level in the surface crack, the scaled extensional stress, and fracture scale fracture toughness, which shows which relates to the ice shelf thickness. Any point in a shaded region, so below the curves, is in a shows an unstable condition. So if we have a very small initial crack, that crack will propagate all the way through the shelf and we get a carving. And any point above this curve is in a stable situation. So of course, we have more interesting stuff to show, but unfortunately no time. So thank you for listening, and please contact me if you wanted to hear more or had more questions.
Thank you. Thank you, everybody. I think we should just give another round of applause to all of our virtual posters. Those were fantastic. Thank you, everyone.